In this video, we're going to talk about how to graph logarithmic functions. And as a result, we're going to talk about transformations. Suppose you're asked to graph the function y equals -3 log base 7 of 4x minus 8 plus 9. Let's discuss a strategy. The argument of the log is the part that is in the bracket, i.e. the quantity we're taking the log of. So in this case, that's 4x minus 8. We then multiply that output by a, so in this case that's -3, and we add c, and in this case that's 9. Now the thing that we input to the parent function in our transformation strategy is always k bracket x minus d. So since our parent function is y equals log base 7 of x, the 4x minus 8 represents k bracket x minus d. In other words, the k value will be 4 and the d value will be 2. Okay? So what we would do to state it a little more clearly perhaps is rearrange that function as shown in step 1. And we'll say a is -3, k is 4, d is 2, and c is 9. Now we want points on the parent function. So that means we want points on the function y equals log base 7 of x. So you might think, well, how can we do that? Well, this is interesting. What we're going to do is use the inverse of that function. Now, the inverse of the function y equals log base 7 of x is y equals 7 to the exponent x. It's pretty easy to make a table of values out of y equals 7 to the exponent x. We'll use -1, 0, and 1 as our default x values, and we'll get y values of 1/7, 1, and 7. So what this means is that the point -1, 1/7 is on the inverse of y equals log base 7x, 0, 1 is on the inverse of y equals log base 7x, and 1/7 is on the inverse of y equals log base 7 of x. Well, what that means then is that points that are actually on y equals log base 7 of x will just have the x and y columns reversed. So we can say that the point 1/7, 1 is on the parent function. We can say that the point 1, 0 is on the parent function. If you don't see what we're doing, we're literally just switching the columns. And finally, we can say that the point 7, 1 is on the parent function, y equals log base 7 of x. We've got 3 points on the parent function, and as you know from experience, that's a pretty good way to do it. Now, that takes care of step 2. So I'll read step 2 just to really solidify the point. We want points on the parent function, so we will create a table of values to determine points on the inverse of the parent function using x values of x equals -1, x equals 0, and x equals 1. And then we'll switch the values in the x and y column of that table of values to give us, since we got points on the inverse, switching the x and y columns will give us points on our actual parent function. In our example, the inverse of the parent function y equals log base 7 of x is y equals 7 of x. So we'll make a table of values for y equals 7x, then switch the x and y column, thereby giving us points on the actual parent. Okay, getting to step 3. We'll then apply the mapping formula that you're very familiar with. xy maps onto x over k plus d, ay plus c, or you can use other methods that you've learned in previous grades from other teachers. Those are awesome methods. We're going to apply that mapping formula to the points that we got in step 2, which are these points right here, after switching the values. So those are the points right there. And then we're going to remember that we'll have a vertical asymptote at x equals d. Now, it might help to explain why this is. Every logarithmic parent function has a vertical asymptote at x equals 0. If you don't remember that, just actually think about how every exponential parent function has a horizontal asymptote at y equals 0, and then logarithmic parent functions are inverses of exponential parent functions, so y becomes x. So the logarithmic ones end up having switching the y with an x gives us a vertical asymptote at x equals 0. That's one way to think of it. But anyways, as we now know, every logarithmic parent function has a vertical asymptote at x equals 0. And now when you take that value of x equals 0 and put it through the mapping formula part that says x maps onto x over k plus d, we get 0 mapping onto 0 over k plus d, which means 0 over k is just 0. So 0 maps onto d. So the original asymptote x equals 0 becomes the transformed vertical asymptote x equals d. Now, we're going to be stating transformations here too. So in this section, you'll be expected to graph a transformed logarithmic function and also to state the transformations that occurred to the parent logarithmic function. Now at this point, let's review how to verbally state transformations. We've already gone through this from our presentation in the transformations unit in the previous video. The value of a, if a is greater than 1, then we know there's a vertical stretch by a factor of a. If a is a positive number but it's less than 1, there's a vertical compression by a factor of a. If a equals 1, there's no transformation. And if a is less than 0, we have a reflection in the x-axis. And then we look at the magnitude of a, and we go back using the magnitude of a to our first 3 points. Okay. If looking at the value of k, if k is greater than 1, then there's a horizontal compression by a factor of 1 over k. If k is a positive number but it's less than 1, then there's a horizontal stretch by a factor of 1 over k. It's 1 over k because if you recall in our mapping formula, we divide by k, meaning we multiply by 1 over k, and that's what factor means, multiply. If k equals 1, there's no transformation. If k is less than 0, in other words, k is negative, then we know there will be a reflection in the y-axis, and then we'll use the magnitude of k rather than k itself, and we'll go back up and we'll state whether there's also a horizontal stretch or compression based on the first 3 bullet points. Now the value of d. Remember that to determine the value of d, you need to make sure that k is factored out in the input of the function, and you also want to make sure you change the sign in the bracket. So if d is greater than 0, there's a translation to the right. If d equals 0, there's no translation. If d is less than 0, then there's a translation to the left. And finally, the value of c. C is perhaps the easiest of all to state the transformations of. If c is greater than 0, there's a translation c units up. If c equals 0, there's no vertical translation. And then if c is less than 0, there's a translation down. And if c is less than 0, we use the magnitude of c in our verbal description. And then we have default settings. The default settings of a and k are 1. So if a and k are not apparent, their assigned value is 1. The default settings of c and d are 0. So if c and d are not apparent, their assigned values 0. And there's explanations there. Basically, a and k are values that we multiply or divide, and the identity for multiplication or division is 1. And c and d are values that we add or subtract, and the identity for addition and subtraction is 0. So let's graph the curve shown. Y equals 6 minus 3 log base 2 of 4x minus 20. First thing we want to do is state the coordinates of 3 key points. So what we're going to do is we're going to say, okay, our parent function is y equals log base 2 of x. We recognize that it's hard to come up with points on that function, so we'll consider the inverse, y equals 2 to the x, and we know how to do this from grade 11. We come up with points on the inverse function, y equals 2 to the x, and then what we can do is switch the columns, and by switching those columns, there's a really roundabout way of doing it. By switching those columns, we're now able to say 3 points that are on the parent function for this particular curve of y equals log base 2 of x. Okay, so here we go. This is it written out a little more nicely. Points on the curve. Switch the values from one column to the other. And now we've got points on the actual parent function for our case. Okay, now That curve can be rearranged as shown. So the A value is -3, the C value is 6. This should be a 20 here, little typo. But that 4x minus 20 becomes 4 bracket x minus 5. And our C value here, it says 5 there, but it's actually a 6, a second typo here. So what we have is an A value of -3, a K value of 4, a D value of 5, and a C value of 6. And we put our points that are on the parent function of y equals log base 2 of x through the mapping formula, and we come up with 3 points on the transformed curve. Now, we also know the vertical asymptote is x equals 5. If you recall, we said earlier the vertical asymptote will always be at x equals d. In this case, d is 5, so our vertical asymptote is x equals 5. We plot these 3 points. And what we have are what we have here, if it helps us, one thing we wanted to point out, if you only have these 3 points right there, those are the 3 points that we got by using our mapping formula and the 3 key points that we came up with. So you might think to yourself, well, geez, that's not quite enough for me to be able to properly graph this curve. I should have a little more. So what you can do is always use more points. Now, how can you use more points? Well, the curve, if you recall, a couple minutes ago, we were using the curve y equals 2 to the x, and then switching the x and y columns to get points on the parent function y equals log base 2 to the x, log base 2 of x. So what we're going to do is we're going to come up with additional points on the curve y equal 2 to the x, and then we're going to switch the x and y coordinates of those to come up with the inverses of those points. So 2, 4 becomes 4, 2, 3, 8 becomes 8, 3, and 4, 16 becomes 16, 4. And that's going to give us more points on the curve y equals log base 2 of x. We can then take the point 4, 2 and plug it through the mapping formula and come up with the image point 6, 0. The point 8, 3 is on the point, the image point is 7, -3. And 16, 4, the image point is 9, -6. Now, was this necessary to put those extra 3 points through? No, it was not. But by doing that, we came up with these 3 circled points. The ones with the arrows were the 3 originals. The circled points are these new 3 points that we just got. And now, using that, we can actually come up with a much better description of the curve, a much better sketch. The parent function is y equals log base 2 of x. And now to state the actual domain and range, or sorry, to state the transformations, since a is -3, we have a reflection in the y-axis and a vertical stretch by a factor of 3. Since k is 4, we have a horizontal compression by a factor of 1/4. Since d is 5, we have a translation right 5 units. And since c is 6, we have a translation up 6 units. Our domain is x greater than 5. Our range is y element of the reals.